this video, we're going to talk about the invariance of the four-vector x, y, z, and ICT under Lorentz transformations. This four-vector here is actually the coordinates of an event. We call it an event in the language of theory of relativity, and that is a particular point in space time. Now, in order to demonstrate that the coordinates of this event, that the four vector, which is given by these components, remains invariant. In other words, it doesn't change under Lorentz transformations. We have to first discuss what Lorentz transformations are. Now, in classical physics, if you have two frames of reference, particularly two inertial frames of reference, which are in relative motion with respect to each other, the transformation rules from the coordinates of one system to the other is given by Galilean transformations, or some people want to call it Newtonian transformations. And we know that it's accurate, it works as long as the velocities involved are not comparable to the speed of light. When this is the case, let's say the two frames are in, let's say, relative motion with respect to each other, Newtonian mechanics, Newtonian laws of motion will be valid in both systems, of course, and observers in both systems can easily communicate with each other using Newtonian transformations. Today, however, I'm going to talk about the more general case in which the frames of reference are in relative motion with a constant velocity, which makes both frames of reference to be considered inertial frames of reference. And the speeds involved, we would assume them to be speeds comparable to the speed of light. Lorentz gave us the correct rules of transformation. And right now I'm going to write them down for this particular scenario. Let's consider two frames of reference, both of them inertial frames of reference. One I call S, the other one I call S prime. And let's say S and S prime are in relative motion with respect to each other. And without any loss of generality, let's consider from the perspective of system S, S prime is drifting away with a constant velocity, which I show here by U, along the horizontal axis, X prime. Now, you should always consider the fact that we live in a four-dimensional world. Let's say microscopic objects that we're talking about. We're not looking into the realm of subatomic particles. We're just looking into ordinarily sized objects. You can identify a particular event by assigning 3 spatial coordinates and 1 temporal coordinate. Now, to make things simpler, here I'm just drawing 2, let's say, systems of coordinates in a 2-dimensional fashion. Obviously, I cannot show 4 dimensions on a 2-dimensional, screen. So I'm just using the XY coordinates and the X prime, Y prime coordinates from both systems, okay? But you should always remember that this is actually a 4-dimensional space-time problem. And the relative motion between S and S prime is happening along one of these components or coordinates, if you would like to call them, namely along the XX prime direction. All right. So since we're discussing in the realm of the special theory of relativity, it is easy to understand that for an observer that is at rest in system S prime is appearing to be moving away with everything inside it, drifting away with this velocity u. And likewise, if someone is doing the measurements in system S prime, if he is at rest in system S prime, he or she would see that events in system S are drifting backwards away with the speed of minus u. All right, so that is something that we have to consider first. Now, Lorentz transformations, as I said, these are a set of linear transformations that allow us to communicate between these two frames of reference. So in other words, if I have an event happening somewhere in space-time, measurements of the coordinates of the event in system S prime and measurements of the coordinates of that event in system S are generally not going to be the same, but through a set of linear transformations, both systems can communicate, or both observers in both systems can communicate. One more assumption before I write down Lorentz transformations is that, again, for simplicity, we would consider that both systems, S and S prime, their origins, which I will show here by O and O prime, they coincide at the beginning of time in our problem, meaning that S and S prime were on top of each other, and then we allow time to pass, and gradually S prime moves to the right from the perspective of S. So that means this distance between the two origins of the coordinate is actually u times t. So the distance here is u times t. It's a simple fact as a result of the uniform motion between them. So as time goes on, in a linear way, S prime and the distance, let's say, between O and O prime starts to increase. All right. Now let's talk about an event that takes place in space-time. Let's say the event, we will show this by this asterisk here. And let us see what the observer in S prime would measure for the coordinates of this event. Well, let me show that event by P. The observer in S and the observer in S prime both see this event from the perspective of the observer in S prime. The event takes place at the coordinate, horizontal coordinate of X prime, vertical coordinate of Y prime, and then the third dimension Z prime, and a time T prime. From the perspective of the observer in S, he or she would register the coordinates of the event P as X, Y, Z, and T. Now, in order for S and S prime to talk to each other, they must find a way to convert their coordinates of this single event that is taking place at some point in space and at some point in time. And as I mentioned earlier, the proper transformations between these two frames of reference is given by Lorentz transformations. So for this particular scenario, we can write X prime, which is the horizontal component of this event, the horizontal coordinate of this event measured by S prime. And that is given by what S measures for its X, and then minus ut divided by the square root of 1 minus u squared over c squared. The y coordinate of the event would be the same in both frames of reference, because as you see, the relative motion only happens along the horizontal direction. So the y component is unaffected. Likewise, the z component is unaffected. Both observers would measure the same value for z. But what about time? Well, it turns out that the time coordinate is not going to be the same. And in fact, it's going to be transformed in this way. It would be t minus u over c squared times x, and that divided by the square root of 1 minus u squared over c squared. Okay. Now, before we continue further, I have to mention that c is the speed of light in vacuum. Let's say we're looking into this problem in vacuum where the speed of light is at its highest value. And this factor that appears in the special theory of relativity, 1 over 1 minus u squared over c squared, we call this the relativity factor. And we often show this by the Greek letter gamma. And gamma is obviously a function of the relative velocities in the two frames of reference. So in this way, I can rewrite the Lorentz transformations in this form. I can say that x prime is gamma times x minus ut. This is a more compact form. Minus ut, y prime is y, z prime is z, and then t prime would be gamma times t minus u over c squared times x. These are Lorentz transformations. Okay, now back to the topic of this video is what I intend to show you, that this 4 vector here, x, y, z, and t, you would see this I and c appearing here. This is just for making these units to be consistent with each other. So the 3 spatial coordinates are spatial coordinates, as I said. These are in SI units, these are measured in meters, whereas time is measured in seconds. So I bring in a factor of c times t with this I, the imaginary unit, to make them all having units of space, okay? So the c, of course, is the speed of light. I is just the imaginary unit, the square root of -1. All right. So I want to see that these 4 vectors, how these 4 vectors remain invariant under these transformations. Okay, so for that, I'll define the 4 vector in system S prime as x prime, y prime, z prime, and I, C, T prime. And the 4 vector in system S as x, y, z, and I, C, T. And we want to see that these 4 vectors are actually the same in size. Now, 4 vector is a generalization of an ordinary 3-dimensional vector with a 4th component. And through Pythagoras' theorem, we know that the norm of a vector is the square root of the sums of the squares of each component. So in this case, the length or the norm of the 4 vector given by the system S prime would be x prime squared plus y prime squared plus z prime squared plus I c t prime squared. Under the square root sign, and the 4 vector given in system S would also have a norm with a similar mathematical structure. X squared plus y squared plus z squared plus ICT squared. And what I want to show you here is that these two norms are exactly the same. That is the meaning of invariance of these 4 vectors, okay? So let's, in order to make things simple, let us forget about the square root signs right now. In other words, let's look at the squares of the norms and write that in this form. X prime squared plus y prime squared plus z prime squared plus I c t prime squared. And I want to show that this is actually equal to x squared plus y squared plus z squared plus ICT squared. All right. So in order to do this, well, look at the left-hand side. I'll work my way through the left-hand side using Lorentz transformations to end up with the right-hand side. So let's see if it works or not. So here, x prime, I would replace x prime by the transformation into system S. So that is x, that is gamma times x minus ut, the whole thing squared, plus y prime was the same. I'll go back to show you. You see y prime is the same as y, so I will, for y prime, I will just replace it by y. And then likewise, z prime would be the same as z. And then ICT prime squared, well, I squared is minus 1, right? You know that I is the square root of -1, so I squared would be minus 1. So I squared turns out to be minus 1. And then c squared, and then t prime squared. For t prime squared, we would again use the proper transform of time in the Lorentz transformations, right? So it will be this guy squared. So here we have gamma times t yeah, it's gamma times t minus u over c squared times x. And this is what we end up with. Now I have to open up these or expand these squares here and work my way and possibly simplify things in order to end up with this. So let's see if it works or not. So here we have gamma squared times x squared plus u squared t squared minus 2x ut, and then plus y squared plus z squared minus c squared. And then here again, we have a gamma squared times t squared plus u squared over c to the 4th power x squared minus 2tux over c squared. Now let's try to simplify things further. So here I have gamma squared x squared plus gamma squared u squared t squared minus 2 gamma squared x ut plus y squared plus z squared minus c squared gamma squared t squared minus c squared cancels c squared from the denominator of the second term, leaving us with a u squared over c squared, and then times x squared. And then this c squared obviously cancels this one. So we end up here with minus, there's a minus here, there's a minus here, so it'll be a plus gamma squared tu x. Okay, now let's first look into see if we can even simplify these even further. Let's see where I have x squares. So here I have the first term has an x squared. This term here has an x squared. So I guess I can actually factor an x squared gamma squared. So here I end up with 1, and here I end up with minus u squared over c squared. On the other hand, I can easily see that this term is exactly the same as this term, but with the opposite sign. So these two terms cancel each other. And as for y squared plus z squared, I'll keep it as it is. So here we have y squared plus z squared. And then here, I can actually factor the common term gamma squared t squared. So here we get plus gamma squared t squared, and I have u squared minus c squared left. Okay, so things are starting to get a little bit simpler. Now, if you recall what gamma was the relativity factor. It is 1 over the square root of 1 minus u squared over c squared. So gamma squared would actually be 1 divided by 1 minus u squared over c squared. So here I see 1 minus u squared over c squared. I can replace that by 1 over gamma squared. On the other hand, here I see a u squared minus c squared. Let's see where I can get that from. So if I take this common denominator here, c squared, I have a c squared minus u squared here over 1. In other words, this would be c squared divided by c squared minus u squared. And therefore, c squared minus u squared would be nothing but c squared divided by gamma squared. So if I see u squared minus c squared, that is actually minus gamma squared over c squared. Okay, so let's rewrite the square of the norm of the 4 vector again. So you can see here that there's a gamma squared right here. So that gamma squared can cancel this gamma squared. But on the other hand, here we have a, let me fix this here so that, yeah, so here you see we have c squared minus u squared is c squared over gamma squared. So this would be minus c squared over gamma squared. Okay, so you can see that a gamma squared and a gamma squared cancel here. So we will end up with x squared plus y squared plus z squared minus c squared t squared. And one last step, I can take this minus c squared t squared and write it as ICT squared. So I end up with x squared plus y squared plus z squared plus ICT squared. And this is what I wanted to end up with. So I'll zoom out a little bit so that you would see we started from the left-hand side and we ended up at exactly the right-hand side which we were trying to show. So the bottom line here is that Lorentz transformations, these set of linear transformations, actually preserves the norm of the space-time 4-vector x, y, z, and ICT. So I hope that you've learned something from this lecture, or this short video. It was just a simple derivation. When you're playing with these transformations, please be cautious, because you can simply make careless mistakes. And sometimes the algebra, it's not difficult at all, but sometimes you might miss a minus sign, or like this case when I first wrote c squared over c squared minus u squared. When you're plugging things back, make sure that you don't make any small mistakes. So please let me know your thoughts about this video in the comment sections. Don't forget to subscribe to my channel, and I will be back next time with more physics content. Until then, take care of yourselves.